Hi everybody, thank you for being here. So my name is Basha and I work for a company called Criteo, which is in the ad tech industry. As far as I'm concerned, I'm a SRE in the network load balancer team, and we're in charge of the load balancer, service mesh, and service discovery at Criteo. And today I will walk you through our journey of automating and improving our load balancing stack using around HAProxy, the challenges we face, and how we address them. So here's the agenda. I will start by telling you a bit about ourselves, and then there will be two parts regarding automation to reduce HAProxy reloads, TLS certificate automation, service provisioning, and following by two parts on CPU reduction with TLS resumption and CPU optimization. So who are we? So Criteo is the largest independent ad tech company and was founded in 2005 in France. The company is operating in 19 offices and has more than 3,500 employees. We participate to about 9 billion bid requests per day. And to do so, we need to have the right infrastructure. So the foundation of our business is the infrastructure. We're not a cloud-based company. We have our own bare metal infra spread over 6 data centers on 3 continents. And you can see a few indicators on our available resources. We handle more than 1 million CPU cores. And we have 30,000 servers, and amongst those servers, 2% are dedicated to load balancers. Here are a few more metrics on the LB side. We handle roughly 23 million requests per second. The ingress is 990 gigabits per second. We receive a lot of bidding requests, and the egress is 970 gigabits per second. Those are mostly images we display on the internet. So updates since last time. 6 years ago, at the HAProxy conference 2019, we did a talk about how we moved from a ticketing system to LB as a service. The talk was pretty much how we automated from the toll task and moved out from a big load balancer appliance or vendor-locked appliance on many HAProxy running on commodity hardware. At that time, we're running on HAProxy 2.0. Since then, as you could see in this illustration, a lot of things have gained in maturity. We have fully replaced the L4 stack by LVS with Keep LFD. We've started using EVPN overlay to fix traffic imbalance. We are still using HAProxy for our L7 stack, and we are running on HAProxy 3.1 today, as of today. We've introduced a caching system using Varnish in between HAProxy. We even provide a local CDN to our internal customer. We're still using console as service discovery for the service discovery. And regarding the containers, we have some Apache Mesos and Kubernetes containers. So for the backends, we have a distributed architecture with tons of microservices. We have more than 100,000 containers running on Kubernetes and on Apache Mesos. We are currently in the process of migrating everything from from Mesos to Kubernetes. And we still have a very few applications running on bare metal nodes. So this introduction should have given you an idea of what we are managing for our load balancing system. And our end goal is to provide the best quality to provide a load balancer as a service. Therefore, we are constantly looking for automation and performance. So HAProxy version 1.8 introduced the seamless and hitless reloads, which improved the user experience to avoid downtimes. So you can find more information in the link below. But reloads comes with a cost. It requires CPU and memory to handle the old and the new requests. And reloading under heavy traffic conditions could impact the load balancing performance. Therefore, the less reload you have, the better the performance is. Also, it has an impact on the Prometheus counters, which are resetted. So there's a work in progress in the HAProxy team to fix those. So in the next part, I will talk to you about automation to resist reloads with TLS certificates automation and server provisioning. So TLS certificate automation. So we manage more than 5,000 certificates for which we apply a 3-month validity. And the certificates are automatically renewed before the expiry date. And we're always trying to keep our stack up-to-date security-wise, as confirms the A+ grade given by Qualys SSL Labs. So this can sound pretty complex, but we have automated all these parts. So to achieve this, the workflow is the following. So we have the certificate provider process, which is in charge of the lifecycle of the certificates. It interconnects with third-party providers like DigiCert or Let's Encrypt. And the role of the control plane is to periodically renew, pull the certificates, and notify any new events to the provisioners. So those two components you have seen are running as microservices on Kubernetes. And the last component is the provisioner. They are running on the same server as HAProxy, and the main role is to configure statically and dynamically the local HAProxy instance. So let's now have a look at the config part. As you might have guessed, the certificate configuration is done on the front-end level using the CRT keyword. And here's an example with the front-end name FTD1. And on the HTTPS binding line, you can see that a CRT parameter pointing to /etc HAProxy TLS FTD1. And this refers to a folder in the file system and containing all the certificates. So you might be wondering why we have so many files. This is simply, it could be for different type of signatures, ECDSA or RSA. They can contain different domains. You can also have a more specific and a less specific certificate, for example, a wildcard. And they could be also the older and newer certificates, because when we renew the certificates, we renew when the old one is still valid. So by passing a CRT keyword to HAProxy, HAProxy will choose the right one following the incoming request. So how does it work at the runtime? Let's say we receive the certificate in blue for this frontend. First, we write it into the file system. So the reason to do that is because the file system has to be in sync with the runtime. Else, in case of reload or restart of the HAProxy process, you might lose your data. Then you need to allocate the certificate using the new SSL cert command, followed by set SSL command with the content of the certificate. And since it's a transaction, you need to commit it. And the final step is to add the certificate to the CRT list with so here, /etc HAProxy TLS FTD1, which correspond to the name of the folder. So in total, you have 4 steps. So something I didn't mention here, the certificate provider process is in charge of doing the cleanup of unused and expired certificates in the file system. So what are the benefits? So this drastically reduced our process reload, and we have none during renewal. With more than 5,000 certificates with different expiry date, we have roughly around 100 renewals per day. And thanks to our automated process, we have control over our certificates. For example, it's easy to invalidate those. And also, we are pretty confident with the lifespan reduction. I'm not sure if you heard about the 47 days validity reduction, which will happen in 2029. So this concludes the TLS certificates part. Now let's go on the second part to reduce the reload, the service provisioning. So since HAProxy 1.8, the way to provision servers was using server templates. So what are server templates? It's pretty much a placeholder to indicate to HAProxy that a certain number of servers could be pre-provisioned for a given backend. So in this example, you can see that the backend BE DEMI app has pre-allocated 4 servers from index 0 to 3. So this can look confusing at first, but if you extend it, this is equivalent to the following. here you have the server, you can see server 0 to server 3 and there's, for example, the server template SRV is a prefix, and then at the end you have the suffix. Therefore, you have SRV0, SRV1, SRV2, SRV3. And now this is how it looks in the runtime call. You have server 0 to server 3 in main state. Now, knowing all this, to provision a new server, you simply replace an unused server using the set command. One of the limitations of this model is that if you fill out all the servers, SRV0 to 3, you need to update the server template in order to extend the amount of server you can handle. And therefore, you need to reload HAProxy. This is one of the limitations. So this was a good enough solution until our users started to use what we call the autoscaler for the application. So we started to have the following pattern, application instance-wise. So here you can observe an increase of 100 instances. And during the morning, you can see that increase from 150 instances to 600. So you can imagine that using server template is not very well adapted for our pattern, as it needed to many reloads. So here comes the dynamic server API, a feature which has been available since HAProxy 2.5. I know that some people are still using 2.4, but yeah. So let's take a look at the configuration part. First, it was a design choice. There's no more default values. So you can't set default values. Possible for the servers. You need to specify all the values at the server line, and therefore remove the default server option. So here, for example, we have a new server inserted. It has a real name. So as my server for demo. So no more SRV plus index. And since there's no default values, you need to put everything here. The weight, the address, the port, max on, whatever. One of the great parts with dynamic server is that since we can now have name server, we can have a better logging. Indeed, in the past, we used to put the IP and the port of the container instead in the field user.srv. And in case of issues with container, it was kind of complicated to find the right physical server to investigate. So let's now try to add the server described 2 slides ago. So the runtime call is done in 3 steps. First, you need to add the server. So during this call, you need to pass all the options in the same line. So you have here the address, the weight, the ID, and so on. And then you need to enable the health, and then enable the server. And something which is very specific for our usage is that we explicitly set the initial state to down, and let the health check update the status of the server once it's ready. And here the server appears instantly on the runtime. Updating an attribute is as simple as calling the set server command. So here we updated the weight from 10 to 30. So no reload required. Deleting a server requires slightly more steps. First, we disable the server so that it doesn't receive any new connection. Then we need to shut down the session for all existing sessions for the server. And after that, we need to wait for the server to become in removable state. So we wait up to 100 milliseconds. And then if the previous command is successful, then you can delete the server. And you can see in the runtime API output that there's no more server. Something I didn't mention is that we enable the severity as number, meaning that each command I run before returns an integer. So something below 3 means that it's in an error status. And following the previous command status, we can decide whether or not to execute the next command. So I wanted to make a general remarks which is valid for any runtime call, not only for servers. When you update using the runtime API, it doesn't update the files on the disk. meaning that you need to write into the config file or the any files, certificates, whatever, all the stuff you pushed into the runtime. And this is to avoid any loss in case of process restart or reload. So what are the benefits? So we drastically reduced the reloads, which helped to improve the resource consumption. Indeed, like I said previously, a reload could be expensive, and thanks to the Dynamic Server API, we went back to have a more predictable resource usage on our system. And this also improved the metrics, since reloading reset the promise metric to 0. And another big win for us is that, I don't know if you remember the first slide I showed you, we have some varnish instances. And for varnish, we need to preserve the consistent hashing. So every request has to go to the same, for a given pass, it has to go on the same instance. Therefore, using the dynamic API, we're able to set the ID parameter. On our way to Dynamic Server, which we started early 2024, we faced some issue, and we had some crashes and so on. And we thank HAProxy team for having fixed those very quickly. So this concludes our part on the Dynamic Server. Let's now move on the next topic to reduce CPU usage. The first topic is using the TLS session resumption. So the idea behind TLS resumption is to be able to resume a TLS session despite HAProxy node being down. So in this diagram, you can see that the user request goes on the LB, which is in red. And since the node became unreachable, the request is being redirected to the LB, to the pass in blue, and with the TLS session resumed. And this is achieved thanks to the keys that are shared amongst all the HAProxy nodes. Overall, this saves some CPU time thanks to the reduction of cryptographic operations involved on a full TLS handshake. I think this is something William just mentioned before. So let's take a look at our processes workflow. So the control planes generates a blob, and so it's very much randomly generated values that are used as base for the TLS keys. Using these blobs, each provisioner computes the TLS keys. So internally, it uses a shared key amongst all the provisioners, and it updates the local instance of HAProxy using the runtime API. So in total, you have 3 steps. On the config side, to declare the TLS key, simply add the keyword TLS ticket keys keyword. And here, it should point to the file system, to the file in the file system. So what are the benefits? And some remarks. So something which is important is like using our control plane, we rotate the keys periodically, and this is highly recommended, else the forward secrecy is compromised. So I invite you to read the documentation of HAProxy, which explains clearly this part. And following the control plane periodic updates, using runtime, the command is as simple as set SSL TLS key with the name of the folder and with the content. Here you have an example of the content. We have 3 keys. And this has to be done on all HAProxy instances within the same time frame. So as always, the good part is that there's no reload. And here you can see the percentage of TLS session reused. On our stack, we have pretty much 30% reuse. And I don't have the exact number of CPU saved, but I invite you to read the blog post, The State of SSL Stacks, where you have a bench on this. So now let's go on the last part, which is CPU optimization. So let's start by laying down the context. Historically, a CPU was a physical component located on the motherboard. With the quick evolution of technologies with multi-core, hyper-threading, hardware, and software naming, the term CPU is difficult to map to a single concept. On our server, we use AMD EPIC 7502 Zen 2 CPUs. The reason for this choice is to have the best ratio performance, power, and cost. And this CPU is well adapted for virtualization and high-performance computing workloads. So in this image, you can see a near-infrared photograph of the CPU. Let's now dissect the different parts. If you look at the image, I've highlighted two parts. So the first part is a core complex die, CCD. It's a chiplet that contains up to 8 CPU cores. It provides the computing power. And in the middle, you have the I/O die, a chip with no cores, only I/O functions. And its role is to connect the CPU cores to memory, storage, and other devices. And it also ties the 4 CCDs together. And the CCDs are composed of core complex, which are CCX, and you have 2 per CCD. And a CCX is a group of core which within a CCD sharing cache. This allows fast data sharing between cores. So each CCX contains 4 CPU cores. It starts from 1 to 4 on the left and goes up to 29 to 32 on the bottom right, which gives a total of 32 CPU cores. So you might wonder why I'm showing you all of this. Simply because data sharing across CPU could be expensive. Indeed, if you consider T being the data latency between 2 CPU within the same CCX, sharing data across CPU CCX within the same CCD is 4 times higher, and across different CCDs is 6 times higher. On our server, we dedicated the last CPU, here CPU 32, to the control plane components. So here, I showed you earlier that we had some provisioner, and they are pinned on the CPU 32. The reason we do that is to avoid messing up with HAProxy processes. So our current configuration is pretty simple. We allocate 31 threads and 1 thread per core, right? So our intention was to avoid thread starvation. Therefore, attributing 1 thread per CPU one CPU per thread was acceptable. So here's a capture of the htop command of one of our server. You can see that each CPU is attached to 1 CPU core. Sorry, each thread is attached to 1 CPU core. And the last CPU, CPU 31, because it starts from 0, runs our control plane. And also it starts the command using systemd. Also, if you remember the architecture I showed you earlier, we have a varnish instance installed on the same server as HAProxy, which explains the usage of the RAM. So knowing all this, our aim is to always get the best of the system resources. Therefore, we started to test a recent feature introduced by HAProxy. In HAProxy 3.2, which has been released last week, there are some options to control the CPU. Allocation policy in an automatic way. Here we have the following. We drop CPU 31 and we do a group by 2 clusters. And this is equivalent to the following. So if you want to type it, you can do it even in version before 3.1. And it can kind of sound complex, but if you look at the image, it pretty much looks, this is the thread group 1 and 2, 3, and 4, the stuff I put in blue. So in total, we have 4 thread groups. Each one has 8 cores, except the last one, which has 7. And in the binary, there's an option to display the thread bindings from the configuration. This helps to get an idea of the config that will be applied at runtime. So we applied the exact same load on a reference node with our nominal configuration, which is 1 thread per core. So using an equivalent traffic, we observed that the node with 4 thread group was using less CPU. This is not a lot, but we can sense that there's a lot of room for improvement and for optimization. And if you look at the context switching, we observed a gain of 20%, which clearly explained by the CPU grouping by CCD. since it doesn't have to go across all the IO die. If you remember the image I showed you like 4 slides before. I know that it's late, but. So as a conclusion, we can say that we will continue experimenting to have the best configuration that works for us. Clearly having policy with auto-computing abstracts complexity. So I invite you to try it. And there's an open discussion on GitHub to gather feedbacks in case you want to try it. So to conclude this talk, we're very happy with all the features that HAProxy provides. And we really much appreciate the release cycle of HAProxy, which is quite fast. And there's like many improvement and bug fixes. And my team, we tend to install the latest version as soon as it is released, so we can give early feedbacks and also experiment new features. And as I explained during this talk, HAProxy is very reactive on bug fixes. And sometimes we can see a bug fixed in the same day. And during all this year, we developed a very close relationship with HAProxy team. And the last point I would like to add is that we are looking forward to have the dynamic backend and frontend, so we could perform the very much automation at all levels. So thank you for your attention. And if you have any question, feel free to ask, but I guess we have only 2 minutes. You might not have time.
Awesome. Great talk, Basha. Thank you. So yes, as you said, we probably do have time for maybe 1 or 2 questions. So if you have a question in the audience, please just put your hand up nice and high. We'll get a microphone over to you. There is one over here. While that's making its way over, I'll just ask one from the stream. Your team uses the HAProxy runtime API to create servers, set certificates, and set TLS sessions. Is there anything else you wish the runtime API could do?
No, I wanted to add something. Oh, no, okay, sorry. This was the question, right? Sorry, can you read it?
And actually, you may have addressed that one in some of your slides about how you manage your backends. So there is one up here. Why don't we go to the live audience?
Okay.
Just wondering if you're using servers with more than 1 socket, and if you had any issues with NUMA boundaries.
I'm not sure to understand the question. Maybe we can discuss
That was single CPU. Do you use dual CPUs?
Dual socket, I mean, as a backend?
On the HAProxy.
Sorry, I'm not here.
All right, well.
Yeah, maybe we can talk about it, okay.
So, Basha, you'll be around today and tomorrow
as
well. So I'm sure if you have other questions or questions about his talk, you can feel one more? Okay, go ahead. Yeah.
Did you test on any other CPUs?
No, because what happens, like we have a kind of a flavor, which is what we call a base flavor. And we have the EPIC 7502 CPUs. And this is the only server we have in our infrastructure. And we use it for any applications, not only for load balancer, but also for containers or other applications. So no. But I invite you to test it. And give feedbacks.
Great, we'll give it up for Basha. Thank you.
Thank you.
So this is our, we have one